I think another thing, really, really cool thing to think about is these pulsar planets. So a pulsar is basically a type of neutron star. And a neutron star is kind of a dead remnant of an old, really massive star that explodes.
Super, super dense star, right? I used to read that like it was like a teaspoon of it would be like the same mass as a mountain.
Yeah.
Which is crazy.
Right. Just a little teaspoon has the mass, which is incredible, right? That tells you like how dense it is. Literally the most dense things in the universe besides black holes. If you increase the density, and there's an equation for this, if you increase the mass of a neutron star, which interestingly, as neutron stars get more massive, they get smaller, right? Most object, think about planets, add a bunch of mass to the moon, you may eventually get to where the Earth is. Add a bunch of mass to Earth, you may get to Jupiter. Add a bunch of mass to Jupiter, you may get to the sun. Add a bunch of mass to the sun, you may get like a supergiant star. But if you add more mass to a neutron star, it gets smaller. It's like approaching this, this like black hole limit. I don't remember what the exact mass is. I used to have this memorized from my comps exam. 2.25 solar masses. Some theories suggest that it could get up to 3. But basically, if you exceed, if a neutron star, which will be like the size of a city maybe, exceeds the mass of a couple suns, collapses to a black hole, which I think is like really cool.
Yeah, but is that like an actual process that occurs? Like,
well, what's causing a neutron star to
accumulate mass?
Accumulate mass.
Yeah, and what scenario does that happen? Is if there's like 2 in close proximity, or maybe there's because neutron stars would happen after a star goes nova or supernova, right?
Yeah.
So they blown off all of their like outer shell, and this is like the dense core that remains. And then that could continue to have its own gravity and aggregate more mass to it.
Yeah. So, I mean, you bring up a good point. The way that you create a neutron star is through an explosion of a supermassive star. So you think of a star that's much, much more massive than the sun. I forget what that limit is, but maybe it's a dozen solar masses or something like that. And maybe it's a little bit more or a little bit less. I think it's a little bit more. What happens is, while it's doing this fusion inside, it's creating all these heavier elements. Once it starts fusing iron, getting into that region, no longer the outwards radiation pressure can match the inwards gravitational pressure. So like in less than a second, all of it collapses under its own gravity. That collapse squeezes everything together and forms your neutron star. And then it bounces back, right? It's just like a conservation of energy collapses, bounces back. That's the supernova explosion. What's left behind is that core, that extremely dense core. Now, for a star massive enough, you can actually squish it down into a black hole. So a neutron star will come from a supernova of a progenitor star that's less massive than the one that would create a stellar mass black hole. At that point, the neutron star is not really accreting more mass, right? This stuff is getting blown away, and the neutron star is just kind of there. Now, you could imagine if this thing was maybe in a binary pair and there was a nearby star that was getting larger as it aged, it could like siphon off some of that mass. And that does happen for white dwarfs. And one of the types of supernova that exists are not just from a massive star collapsing, but a type 1A supernova is from a white dwarf, which, like the sun, basically, it doesn't ever go supernova. It just kind of sheds its outer layers, but it still has a core, a white dwarf. It'd be a lot larger than a neutron star because it wasn't compressed in that collapse.
Right.
Yeah. Still very dense, though. Not anywhere as dense as a neutron star. But if this white dwarf is being orbited or is in a binary pair with a star that starts to grow larger, some of its gas may start to spill onto the white dwarf. And then if the white dwarf starts accreting mass, something similar happens, but it goes supernova. And this is one of the ways that we judge distances of galaxies. It's because the maximum mass of a white dwarf is the same, again, the Chandrasekhar limit, those explosions are the exact same brightness. So every time you see a type 1A supernova, you know exactly how far away it is from you because you know exactly how much energy is being produced. I say exactly, right? But it's a tight range. So a type 1a supernova in a galaxy that's very close to you is going to appear extremely bright. A type 1a supernova in a galaxy that's very far away is going to look much fainter. But because you know what that limit is, we can use these as what's called a standard candle. So type 1a supernova, really cool thing.
Yeah.
Early on in grad school, I was doing observations one night of just different planets that my research group was interested in. And there was a supernova. And people who study supernova, they can't plan it because you don't know when they're going to happen, right? They just happen. And you realize, oh, wait, supernova's going off. So they apply for takeover time. And I was on the telescope, and one of these groups had a takeover to observe a supernova, which basically meant that I got to observe that supernova. It was really, really cool to see. I ended up being co-author on the paper for making the observations, but I was in the data collection team. It was very cool. So I'll actually show you. If I remember, I'll post it on here too. But I actually show you right now. I have a picture that we took of a screenshot of the guide cam that shows the supernova.
Wow.
So the galaxy is right there. You can kind of see there's a dark disk in the middle of the galaxy. That's just the center of the galaxy, bunch of dust and gas.
Right.
And then the middle bar here, the middle slit, is right on the supernova. And you can see that bright dot is damn near as bright as the whole galaxy.
Yeah, it's so crazy.
That's how energetic these events are. They're for a brief amount of time, they're releasing as much energy as the entire galaxy, which is crazy. Like one star blowing up, rivaling 100 billion stars that are fusing hydrogen and helium. Very, very cool.
Yeah. So what we talked about, though, were these planets that orbit around pulsars.
Oh, yeah. Totally forgot where we were going with that. So you imagine this process of that supernova happening to create the pulsar to begin with. It's so energetic, would not be feasible to think that a planet could survive that explosion. You would think that they would just get destroyed in that, right? Mind you, this explosion is like rivaling the energy output of a galaxy. And so we would not have thought that planets could exist around pulsars. Maybe if like a rogue planet got captured by it, maybe that could happen. Like just a planet that happened to be passing by.
Right.
But it turns out the first exoplanets that we find, 1992, were pulsar planets. They were planets orbiting a pulsar. And the way that we found it out is really cool. So we've talked about the radial velocity method before, where, the Earth is orbiting the sun mostly. But really what's happening is the Earth and the sun are orbiting a common center of mass. And that common center of mass is so much closer to the sun because the sun is so much more massive.
Right.
Well, this happens for any object. Same thing for neutron stars and pulsars. But the way that these planets were detected was because they were able to detect a light delay. So one way to think about looking at a star and seeing if it had a planet is looking at the spectrum slide as it moves towards you and away from you. We see the light from the star get red shifted and blue shifted. But you can imagine a pulsar. You're not looking at visible light. You're looking at radio waves. That's what the pulse is, because it has like a pulse of a beam of light that points at you. So, imagine a planet orbiting this thing, but they're both orbiting the common center of mass. So the pulsar is doing this, right? So as it beams and the light points at you, sometimes it's closer to you and sometimes it's farther away. And because light travels at the speed of light, which is always constant, you could detect that. It's like nanosecond difference of the beam hitting you when the neutron star is closer and the neutron star is farther away. And the interpretation there is that the thing is actually moving because there's a planet orbiting it. Does that make sense?
Yeah.
So it's like the same concept as radial velocity, but you're detecting a difference in the beam of light hitting you. That's a radio wave, which is really cool. And these are the first planets ever found. The first exoplanets.
Right. But you weren't able to visually see these things. You just were able to detect this difference.
Can absolutely not see them.
Interesting.
It's inferred that there are planets of certain mass that are causing the pulsar.
But it could be anything of a certain mass, right?
Yeah, it could be, in theory, it could be any object that is I think the first one had a couple planets that were like maybe like 4 and 3 Earth masses, and then there's another one that's like half an Earth mass or something. So, yeah, you could also explain this by some other mysterious object that was 3 or 4 Earth masses. We only know of planets to fit that regime.
Yeah, and I guess we talked about the possibility of civilizations popping up around these. It seems like they'd have to have a lot of ability to tolerate volatility. Like, or any planet any civilization that lives on a planet.
So the question is, did the planets survive the explosion? Because there's 3. So now you get into an area where it's like, I don't believe that rogue exoplanets found this neutron star if there's 3 of them.
Right. And because that would suggest that they just were gravitationally like drawn to this neutron star.
That would suggest that randomly 3 rogue planets were just right there and able to land in a tight, stable orbit. Does not make sense for that to happen. I would believe if like there was one that was really far away that was orbiting, but 3 of them all in the same plane just doesn't make sense.
Yeah.
So it's like, did these planets survive that explosion? That's one way you could describe them being there. Another way, which is really interesting, is that in the explosion, maybe there was an opportunity to undergo a second round of planet formation. So in the explosion, all these heavy metals are created. What if there's also an accretion disk? There's sort of a period where there is accretion disk for the neutron star and for new planets to form, and that these are like second-gen recycled planets orbiting the pulsar. In that case, it would be hard to believe that like life would be able to emerge there.
Yeah.
Because of the extreme volatile environment.
Yeah, exactly. Yeah, but I guess maybe a possibility could be that that's not somewhere that you set up camp to live, but it could be a place where you try to harness energy.
Maybe. Yeah. If you're so advanced that you've like exceeded, which is kind of hard to think about, but who knows, that you've like exceeded the limits of what your star can do, and you need to start harnessing energy from something like a neutron star. Interesting. I don't know what that would look like, but you may find one that had planets. The thing is we don't find a lot of planets around pulsars, which is also interesting because usually in astronomy, when you find something early, you found something that's common.
Right.
Because there's so much stuff out there, balance of probabilities. We find planets around a pulsar first. Pulsars must be rich with planets. But that's not true. Half of them that we know of were in that first system. We know of only, I think, 3 more. Wow. It's either 3 or 4. So half of them were the first little batch that we found.
Wow, that's anomalous. Yeah, and then the other ones maybe have like 1 or 2 or...
Yeah, I don't know what the other system... If the other systems, I don't know them specifically. It's something like that. I don't think it's another 3 planet pulsar. I think there may be a couple that have like 1.
Wow. That's crazy, man.
Yeah, super interesting. So with that being said, I would almost believe more that if the planets could survive the explosion, life found a way to like go deep within the planet and like survive that way, maybe. Maybe like if the planet could, if it is the fact that the planets survived as opposed to accreting afterwards. But it's not totally clear. I think most people favor that there was a second round of accretion for the planets, and basically that the planets reformed. So these would not have been planets that existed while the star was burning.
Gotcha. So the planets then would kind of potentially been like exploded apart, but then they reformed. And neutron stars are usually pretty old anyway, right? Or they can be. Their ages can range pretty widely, like more than regular stars, right?
Because neutron stars only form from really massive stars, and really massive stars die young. But I actually don't know over time neutron stars get dimmer, but I don't know what that time scale is.
Well, according to this little video, it's talked about a neutron star being able to last almost forever because they're one of the final states of the massive star, and they don't die the same way that other stars do. They slowly fade away over time.
Right, so they dim over time. Yeah. So it says that the surface temperature continues to drop for the first 1,000,000 years, contends over the next 100 million to billion. So eventually it's a cool neutron star. And at that point, you know, it's not like a pulsar that is, yeah. And, you know, there are lots of neutron stars. We know of pulsars and magnetars, which are specific types of neutron star. But yeah, in principle, a neutron star lasts forever. The problem is it cools and dims and eventually is something that you don't see. You could probably detect, because it's massive, maybe it's like doing some sort of space-time warping of the light around it. But as it gets dimmer, it becomes impossible to see.